Good morning, everyone. We're going to go ahead and get started again. This is going to be our second video that we're going to go ahead and look at on chemical foundations. And we want to spend a little bit of time talking about the different units, how we change from unit to unit. And of course, many of these things we'll be covering in class. So if you don't get all of it, try to get your notes down and write down any questions you have, and then we'll be able to move on from there. So starting off here with our different units of measurement. Now, 1960, they're realizing in the science community we're running into a little bit of an issue. And that issue was the Americans were using an English system, whereas the rest of the world, everywhere else literally, was using the metric system. So in order to make sure that everyone was making the same discoveries, using the same information, they developed what are called the SI units, which stands from the International System. But of course, you say it in French, System International. Now, from this, they developed, or they came up with, a certain number of base units that we're going to use throughout all of science. These fundamental units are showed here on table 1.1. These are also in your textbook, from mass to kilogram, meter, and so forth down the line. Now, as we continue to go through this, we're going to realize that there are a couple of things that also come into play. So, now, with these units, one of the things that we had to look at is, okay, well, if I have, seconds, what if it's less than a second, or all these different things? And so what also came up with is a set of prefixes. Now, as you can see on the chart below, that it goes from very, very large, 10 to the 18th in terms of exponential value, all the way to atto, which is 10 to the negative 18. On a regular basis in this class, we won't go that low. So what I've given to you here on the side is a little way to remember how I remember a lot of these prefixes. Take some time, make sure you have them memorized, but not just the names. The names will be important, but also try to remember the exponential notation that's going to go with it. It'll save you a little bit of time when we get into our conversions. But the easy way, and I've used this for years, King Henry died by drinking chocolate milk, making noise. The making noise part was thrown in there at the end, but I'm sure you guys can sort of pick that up. But it's just a way, a little acronym, a little mnemonic device to keep it fresh in your mind. Of course, these are the main prefixes that we're going to use on a regular basis. Pay particular attention to their location because it'll help you to be able to transfer within between units without necessarily having to do a certain calculation. Now, volume. Volume is a little different because volume is something that's used a lot in chemistry. But when we look at it, we didn't see that it was a part of the fundamental units. And that's because it's actually not derived from a regular, well, it's derived from the unit for length or distance. So we're looking at the meter more so. Now, we're going to see that it's a measure of area, as you can see here in the diagram here to the side. Now, the basic ones that we need to remember are the liter and the milliliter. Those are the ones that we're going to come into contact with mostly throughout this year. We see that 1 liter is actually 1 decimeter cubed, which is, again, just looking at the area that the material would take up would allow us to be able to see the actual value, as well as 1 centimeter cubed, or cubic centimeter, would be 1 milliliter. Remember this comparison because we're going to use it throughout the year. We're going to use it a lot throughout the year. Now, this is the next part, I guess, that's going to come into this. With every measurement that you're going to take, with those things we talked about, with volume and length and time, there's always some degree of uncertainty. Now, as it says, most measurements are consistent but not exact. When we look at the chart given all the way to the right of the screen, you notice that all of the values are 20.1 something. But if we look at the diagram, there's no way for you to really tell what exactly it is, whether it's 0.14, 15, 11. The 20.1 is what we're going to call the certain digits. Those are the ones that we can guarantee we fall in line with. But that last digit, that's the one that's going to be estimated. In this case, our accuracy on our burette, which is the tool that's used here, is only goes to the tens place. But we need to go one step beyond that, because as you can see, it doesn't go all the way to the line. It doesn't stop directly on the line, which of course would be perfect. Now, because of this, we have to estimate that last digit. Now, because of this, that's where we get the idea that there's some bit of error involved. Because if we're slightly off, it may not kill us overall, but it will cause a slight difference. And that's building in the idea that one, as humans, we do make errors, but two, just in case there's an issue with the calculation, we can still go through and come up with consistent data. Now, this is going to bring into the conversation the thought of accuracy versus precision. Accuracy, of course, is going to refer to the closeness of a true value. If you look here on the side, on the bottom of the slide, you notice that if we're playing darts, the first picture, A, the darts are all over the place, but the goal is what? To get the bullseye. This would not be a very accurate um, depiction, or if someone was playing darts, that would be a horrible, horrible game. Whereas if you go all the way to C, you notice that the dots are lined up. Most of them are very, very close to the center. Because they're very close to the center, we'd say that person has a very accurate hand, or they have accurate aim. Now, precision, on the other hand, refers to the reproducibility of several measurements. If you look at B, all of the darts are in the same area. Notice that they're very close together, but they're far away from what would be accurate, the goal, the bullseye. This would be precise. As we get our measurements, especially when we get into doing titrations, most of the time you will need your measurements to be fairly accurate. But also, one thing that will help you to understand whether it's accurate or not is whether they are precise. How close are they together, and what were the results that you were getting? Now, with this, we can get a couple of different types of error introduced. And we're going to use the same diagram that we had to sort of understand what's going on. Now, the first type is random error, indeterminate error. This means that the measurement has a probability of being high or low. Now, look at diagram A. This would have a high amount of random error. You notice that there's no defined area where they're far off the mark. It's just all over the place. Versus a systematic error, which is usually going to occur in the same direction each time. So this will be more like B. And B, all of them are in the same location or the same area of the bullseye of the chart. Actually, they've flown off the chart, but this will be a systematic error. All of the measurements are going to be in the same direction. Now, as we continue to look at this, we want to pay attention to the fact that our preciseness, our precision is only accurate if we have no systematic error. Again, our precision is only accurate if we have no systematic error. This is going to be very important as we continue on down the line. I want you to make sure you write down any questions of anything that you may still be having. Moving along. Now, one of the things that we do to account for this uncertainty in measurements is we look at what are called significant figures. And this is basically, as it gives you the reference here on page 15, it gives you the rules of how we assign these measurements importance. How many numbers do we keep? How many do we pay attention to? Make sure also on that same page that you note what it is or what we're used for scientific notation or exponential notation, as it's called in your textbook. It's on the same page right underneath those rules. Now, how we use those information, you can always go and read, but how we use that as far as our calculations. For addition and subtraction, we're going to use the result, the result has the same number of decimal places as the least precise measurement used in the calculation. So given our example, 12.11 plus 18.0 plus 1.1013. If we add it up normally, we write down our answer as 31.123. But there's a little bit of a problem. Our least, sorry, our least precise measurement is going to be the 18.0. So we can only record and be certain of our answer up until that place in our answer. So if we correct it, we end up with 31.3. Now, for multiplication, we're going to do similar, but we're looking at the number of significant figures given in the result. So we have 4.56 times 1.4. Usually, again, we write our answer as 6.38, but we can only be as accurate as our least precise measurement, which is going to be 1.4. So we'd have to round our answer to two significant figures, being 6.4, because 1.4 only has two significant figures. Now, as we're doing this, you want to make sure you remember our basic rounding rules. Same things we've been using since elementary school. If it's 5 or above, we're going to round up. If it's 4 or below, then we leave it the same and we work around it that way. Now, we're going to use the same information as we go into what's called dimensional analysis. Those who have been around or gone through many sciences, you may have already seen a little bit of dimensional analysis. But basically what the idea is, we're going to use these conversion factors to convert between units without changing the original value. We want to make sure that we can go between different units and change, say, centimeters to feet or any of these things using basic algebra to make sure that we don't change the value, but then just have a better understanding of whatever number it is in a different unit. And that's going to be very, very helpful. This is going to be a crucial step, and you'll see as we continue to go why. And we end this video talking about density. And density is a very important property that we're going to look at of matter. One, because it's going to be unique to each substance. Two, because with each of our calculations, especially once we get to our thermochemistry unit, there may be times where you're given the density, and from that you have to derive the mass and move from there. So I want to make sure that we have all the information we need to be able to go ahead and to be successful. Now, the way that we're going to do this is we're going to divide the mass of the substance by the volume that the substance takes up. This could be a liquid, this could be a solid, it could be a powder. All these things can still be calculated. And our units that we're going to use here are going to be grams per centimeter cubed or cubic centimeter, or as you see it written here, grams times centimeters raised to the -1 power. That just means that it would be in the fraction. We're going to continue each of these in practice. We're going to take a couple days, but I want you to write down any questions that you have so that we can make sure they're answered and everything is clear for you. Have a great day, and I look forward to seeing you in class. Goodbye.